In lesson 3 today, we're going to talk about atmospheric pressure, okay? And how do we measure gas pressures and things like that. So this is kind of a wordy definition, there's no doubt about that, but if you can pretend that there is an atmosphere, an envelope of gases extending outward from the surface of any planet. Although gas molecules have very little mass, the gravitational attraction of the planet acts on all the molecules, keeping them near the surface. We describe atmospheric pressure as basically a column of air above a certain place on Earth, okay? So if you can kind of think of a column of air, how big is it, doesn't really matter, but a column of air that extends outward from the surface of the planet, okay? And goes up into the sky, all right? And atmospheric pressure is the pressure that we feel at the bottom of that column, okay? How much pressure is that? All right, so if you went and stood outside right now, you can think of an envelope of gases basically that extend upward in this column above you, okay? These are the things that you would hear about on the news, okay? So somebody's got a weather app for me here? Weather app. Look up the weather today in Okotoks.
I got it.
And what we're looking for is what? What's the temperature anyway?
It's -3.
Okay. Wind chill? No.
Wind is 14 kilometers an hour. It feels like -7.
Okay, that has nothing to do with us. I was just wondering. Okay. On there somewhere, though, it will say this number here. Okay. It'll say something about pressure.
Yeah.
What is the pressure?
1,022.
What units are those?
HPA.
Okay. So I don't know. They've started to do this now. I'm not sure why. That's fine. 1,022 HPA. Okay. And so that's what we're going to talk about today. So if I went outside, you would feel like a 1,022 HPA. Okay. Now you don't really feel that. Okay. But that's basically the pressure, atmospheric pressure outside us today. Okay, and I'll kind of talk about that a little bit here, and what does that look like. And again, you might think, well, that's a really big number. It is, but you also have to consider the units as well. Okay, so we're going to talk a little bit about that. But that's what it is in Okotoks today. If you look up somewhere else, if you looked up Vancouver, for example, okay, it's going to have a different number. If you looked up even in Edmonton, it's probably going to have a different number in most cases. Okay, it depends on weather systems, et cetera, and so on. Okay, but it's going to have a different number there. Yeah.
Edmonton is 121. No, 1,021.
Okay, pretty close.
Las Vegas is 1,013.
Okay. Yeah. Okay, that probably makes a little bit of sense. What about Vancouver? Just out of curiosity. You know Vancouver? Anybody? Yeah. 128.2? No. 10,000. What, 10?
Oh my god. 1022.
Oh, okay. Oh, pretty, well, same, okay. Yeah. And so, I mean, yeah, it'll vary. Okay, it really kind of depends on the weather. So each layer of atmosphere exerts a force on the layer below it. Okay, we're going to talk about that. And because of the weight of the entire column exerts a force on the bottom layer, it is compressed the most. So I'll draw you a little diagram of that. As altitude increases, the amount of air above that level becomes smaller and therefore exerts a smaller force on the air just below it. The higher layers of air are compressed less than the bottom layers. So to draw a diagram about this, okay, so if you basically have an envelope of gases that extend outwards from any surface of the planet. So here's my surface of the planet. We have this envelope of gases, okay, some kind of column there. And what happens is, okay, gases are pretty spread out. So gases are pretty spread out here. But what happens is that layer, so if you can kind of pretend that there's an imaginary layer here, these three gases exert a pressure, okay, because of gravity, everything's being sucked down. Those three gases exert a pressure on the gases below these ones. Okay, so these ones put a little bit of force, put a little bit of pressure on these ones. Okay, those put more pressure on that. Now, if we kind of cut that off there, this group or this layer exerts a pressure on this one. These two exert basically a pressure on the layer below that. Okay? And remember, gravity's pulling everything down, right? So now, when we have gases in here, they get a little bit packed more together. This layer exerts a pressure on this one. These two exert a pressure on this one. These three exert a pressure on the layer below that. So now we're getting these gases that are all packed in here, nice and close together. Okay? And that's what happens in this column of air. Okay? And we measure the pressure at the surface. Okay? Wherever they decide that's going to be at the weather station, they measure that pressure here. Okay? So in our case today, it's apparently 1022. We're going to check again tomorrow if you want. It's different. Okay? You can keep an eye on the pressure. It helps tell you what the weather's going to do. So if they tell you, oh, the pressure is going to increase, that means something. If the pressure falls, that means something. Okay? And that's what a weatherman's job is. Right? 50% of the time, all the time. Accuracy. Yeah. No? Anyway, that's one of the things that they consider for weather. Okay? So that's what happens. Now you can imagine, okay, if you're standing down here, yes, okay, the gases are compressed the most here, yes? So every time you take a breath of air, okay, there is a lot of oxygen around us for us to breathe, okay? Now, what happens when you climb? I'm going to kind of keep this the same here. By the way, what is this? Huh? What's this over here? Yeah. You know how you know it's a mountain? Because it's got a big M. Okay? For mountain. This is what? Sure. Most people say Saskatchewan. Okay? Well, Saskatchewan has a few hills, okay? But yeah, Saskatchewan, it doesn't matter, okay? You can pretend this is this is Okotoks. You go on a hike, now you're here, right? It doesn't really matter, okay? The same thing applies, right? I'm just going to use a different color just because I kind of have a lot of stuff going on here. Now we have these three here, and I'm not saying that there's necessarily more gas molecules there. I'm not saying that. I'm just like, I'm trying to fit more stuff in, that's all. So, there's 4 there or whatever, how many, and then you got this section here, and then you got them all packed in here kind of thing. But if you are standing here, oh, well, that doesn't make sense because there's no air up there currently. But you know what I mean. If you're standing there, he's probably sad. Why is he sad? Remember, I guess I could. There. Why is he sad? Up there? Yeah. Well, there's less, right? It's compressed less as well, right? That's the key here. It's compressed less, okay? It's not necessarily that there's less of it. It's just not tightly packed together, right? So what happens when you climb the top of the mountain? Obviously, it's physical exertion. I get that. Sure. I mean, it's tough to climb the mountain. But what happens up there? You get less oxygen for every breath because they're less compacted, right? So down here, like, oh, that's some high-quality H2O, right? Oh, yeah, that's good stuff. Then you get up here and you're like, oh, that was a good molecule of oxygen. Kind of thing, right? I mean, every breath that you take up there, you're going to get less oxygen in because it's less compacted, right? So you have to work harder, and of course, it's physically exhausting as well. I get that. But that's what's going on there, yes? Okay? He's also sad. Why? Anybody else? Oh, he's standing on the peak with 1 foot. He could fall. It's a pretty good balancing act. only got 1 foot on top here. All right. Okay, but this is called atmospheric pressure. So where's the pressure greater? At the bottom or the top of the mountain? This is important stuff here, so listen. Where's the pressure the greater? Bottom or top of the mountain? Where do you think the atmospheric pressure is greater? Huh? Bottom. Okay. Pressure is sorry. Pressure is higher here, yes? At the bottom. Okay. Pressure is higher because this layer is pushing on this layer, pushing on this layer, pushing on this layer. All that stuff adds up, and the pressure is the greatest at the bottom. Yes? The pressure is less here. Okay? At the top of the mountain. Couple things we need to talk about, I guess. Okay? We'll talk about university for a second, I guess. Since most of you are going to some kind of school, hopefully. Whether you be university or whatever, it doesn't matter. Okay? If you, listen, the pressure is greater here and less there, what do you think that does? Do you know, actually, what water boils at what temperature? Water boils at what? 100. Depends where you are. Yes? Right? Does it boil at 100 in Okotoks? Yes or no? Have you ever done it? I have. I bought a thermometer for my smoker. I had to check to see if it was accurate, so I tried it. Where does it boil in Okotoks roughly? You know? Is it 100? It's not. Why isn't it 100? Where does it boil at 100? Do you know? Yeah?
Sea level?
Sea level boils at 100. Are we at sea level? No. We're higher than sea level, obviously, right? So think about this. As you start to climb up here, does the temperature boil at a higher or lower than 100? So think about that for a second. Is it lower than 100 or higher than 100? The higher up you go. Think about pressure. What happens when you boil water? You're changing it to a gas, right? Think about all the things there. You put a pot on the stove. At sea level, it boils at 100. We'll call this sea level, sure. But as you start to climb the mountain, or you start to get higher in elevation, there's less pressure. Yes? Does it boil at a higher temperature or lower temperature? You can Google it if you want. What do you think? Higher or lower? Lower. You know what it is? It's about 97. Okay? In Okotoks, roughly. And the higher you go, the quicker the water's going to boil. Why?
Because it has a smaller temperature.
Let's talk about pressure. You know, if we're talking about pressure, all this pressure is forcing the gas back into the water, yes? Think of it this way. If you're at, for example, 100 degrees Celsius, sea level, all that pressure pushing down on here is keeping the gas in the water, yes? So it's not letting the water, it's keeping that gas molecules in the water. But as you start to get higher and higher, the pressure becomes less and less. So now when you're about here somewhere, okay, the pressure forcing the gas into the water is less. So it can boil quicker because there's less pressure pushing down on the water. Does that make sense? Yes or no? Okay. If you want, when you go to university, you're going to have a lot of studying to do. Okay? Especially if you're an engineering kid. If you want to take engineering, you're going to have no free time. Your life's over. Okay? If you want to cook noodles really fast, because that's all you're going to be able to afford, okay? Craft dinner. If you want to cook the noodles really fast, you should climb the mountain, okay? Go to the top of the mountain, set up your little cook stove. Your noodles will boil even quicker because you're only going to need to get the water to maybe 95 or 93 or 90 degrees Celsius maybe even, okay? Throw the noodles in there, cook them up real quick, eat them, climb down the mountain, and just think about all the time you save cooking those noodles so that you have extra study time now. Okay? Very handy. Okay? Very handy. And by the way, if you don't like Kraft Dinner, you should start liking it. Okay? It's cheap. It's got that nuclear orange cheese. It's made out of nuclear stuff. Uranium probably or something. They kind of comes in whole wheat now, so it's a little healthier. I think you can get you can get pumpkin spice, right? And that's gross. And you can also get the white cheese stuff, like you can get Mott's or something. Yeah. But yeah. Good. The point is this: the pressure affects, a lot of different things, right? So the more pressure you have here, we're going to have high pressure here. We have to have low pressure up here. Okay, we need to know that for sure. When you climb up a mountain, the pressure is less. Okay, you feel less force. The molecules are less packed together when you're up there. It's harder to breathe, of course. That's why for example, extreme stuff like Mount Everest. When you climb Mount Everest, most people climb Mount Everest with what? A backpack, sure. And oxygen, yes? Because of course when you get that high up, the molecules are so far spread apart, they're not as condensed. So of course you need oxygen to function. Then you don't have enough oxygen, things start to go a little crazy, right? Some people have climbed Mount Everest without oxygen. And lived until they can do that, but it's incredibly tough because first of all, it's exhausting, but you need oxygen, right? So that's when you start to hallucinate things and see things that aren't there, and that's when things go bad, right? Most people climb Mount Everest with oxygen because it's spread apart. You're not getting enough. Your body's, they talk about the body starving itself, right? Okay, so that's important. Part 2, pressure and temperature conversions. So we're going to talk a little bit about pressure and temperature here. This is important for us, okay? Mitch says it's 1022 HPA. What the heck is that? What does that even mean? I've never heard of an HPA. Have you guys heard of HPA before? Yeah, some? Okay, no? But there's going to be some that you do recognize today, so we'll talk about the conversions there. Gases exert pressure when gas particles collide with each other or objects in their path. So right now, gas molecules are bumping into each other, creating a pressure. They're hitting the side of the wall, they're creating a pressure. Okay? Gas pressures can be expressed in different units. There's 4 main ones that we're going to do. They're on the back of your periodic table. So these are there for you, but you have to be able to convert between them. The most common unit is something called a kilopascal. Okay? If you have a car that has the little button on the dash and you push it enough times, you will see the kilopascals pop up for the tire pressure. Yes? Okay? And I'm working on it. Well, we have one of those things, not in my truck, but in the car. Okay? A kilopascal, okay, is a measure of pressure. Usually it says around 240 is probably the number you'd see, roughly, somewhere in that area there. What does that mean? What is 240 kilopascals? Is that good or bad? I don't know, right? We'll talk about that. Mitch said we had 1022 HPA. What do you think H stands for? Hectopascal. Okay? So basically, we're not going to do that conversion, okay, just so you know. But when you look at the weather, they're saying it's 1022 hectopascals, which is their new thing. They used to never do this hectopascal thing, but that's equivalent to 102.2 kilopascals. Move the decimal one place to the left. Yes? Does that make sense? Hecta's here, hecta's here, kilopascals here. Okay? That's what that means, by the way. Okay? We're not going to do the hectare to kilo. I don't care about that. I'm just saying, when you look at the weather, just think, hey, that's actually 102 kilopascals. Okay, that's what it is. They record it as HPAs now. That's their new thing. I don't know why. Okay? But that's what it means. Yeah, okay. Other units include something called atmospheres, ATMs. There's pounds per square inch, or PSI, or as I like to call it. It sounds cool. PSI you've probably heard about before, yes? You know, yes, no? You get the little gauge and we put it on the bike tire or the car tire. It tells you PSIs, right? And 240 kilopascals is about 35 PSI, okay? And we're going to learn how to do that conversion today. How you get from kilopascals to PSI and PSI to millimeters of mercury, which is like old school, okay? Really old school. We don't really use that anymore, but that's an option, okay? Et cetera, okay? Good? So those are the four main ones we're going to talk about. There's a couple other on your periodic table, but I wouldn't worry too much about those. But there is some other ones on there. I think there's 6 altogether, okay? Standard pressure is what we call the average pressure at atmosphere at sea level, okay? And the reason that's important is because, what happened to my, I'm looking for, no. I'm looking for something here. Huh. No. Oh, there we go. Do you guys have this next, or is this farther down? I forget now. That's farther down? Okay. We'll skip that then for now. We're into the example then? Is that right? Okay. Okay. We'll talk about that other stuff tomorrow or whatever. Okay? So this list here is going to be the same that's on the back of your periodic table. Okay? The numbers, here's how the numbers work, so please pay attention because we don't want to mix these up, obviously. If I said, Emily says, hey, I feel like I got 1 atmosphere of pressure pushing down on me today. 1 atmosphere of pressure is equivalent to Ben's 760 millimeters of mercury. Those numbers that goes together. That's the unit, okay? 1 kilometer is 1,000 meters kind of thing. Same kind of deal, okay? And that's equivalent to, like, Anna saying, well, I feel 101,325 pascals pushing down on me. These are all the same things. They're just in different units. And she'd say, well, but I know that that's actually 101.325 kilopascals. That's the same thing because that's just a pascal to a kilopascal is all I did there. I switched the decimal over, or a hectopascal for that matter. And then Brian says, actually, I think it's 1.01325 bar, okay, which is, we don't really use that a lot. Or Mitch's phone issue, 14.7 psi, okay? So all those things mean the same thing, just in different units. These are all in the back of the periodic table. So here's what we're going to do. We're going to set up a little ratio thing, and we're going to convert. They're proportional as well, okay? They are proportional. What that means is, if I had, for example, if I had 101.325 kilopascals, that'd be the same as an atmosphere, okay? If I have 75 kilopascals, look, 75 kPa, I'm going to multiply it by, you could do, Macy suggested yesterday, we could do equivalent fractions. Absolutely. You can set up 2 equivalent fractions. 75 kilopascals, 101.325 kilopascals, and I want to change kPa into ATM. That's the first thing I want to do. So I'm going to say, okay, what is the ratio of these two? What are the same measurements, but in different units? So like I don't remember who I picked on first, but whoever Emily said 1 atmosphere, and then somebody said 101.325 kilopascal. Same thing. So I want to basically have 1 atmosphere here. Okay. These two come from the back of the periodic table. Okay? Yes? I'm going to manipulate those. I might flip them over in some cases. I might keep them like this, depending on what number I start with. I want the kPa to cancel with the kPa. Yes? I'm going to take 75 times 1 divided by 101.325, and it should work out to be, help me out here somebody, please, 0.7 4. Is that right? And I should have 2 significant digits, because I have 2 here, ATMs. And that's how I convert from kilopascals into ATM. I'm going to set up that ratio. Okay, it is proportional. If you want to do equivalent fractions, okay, so if you want to do Macy thing there, which is fine. This is how I used to do it. I'd say, okay, I want to get kilopascals into ATMs. What are the 2 numbers that are the same in kilopascals and ATMs? I say 1 ATM is the same as 101.325 kilopascals. Okay? And then I set up an equivalent fraction. I say, okay, I have 75 kilopascals. Where should that go, top or bottom? What do you think? If I'm going to set up equivalent fractions, what do I need to put on the bottom here, or the top? 75, top or bottom? Bottom, yes? Keep the apples and the apples the same. Ferraris and Ferraris the same, yes? And I'd say, okay, how many ATMs is that? I'd cross multiply probably and solve, yes? So that's an option 2. It's up to you. I don't care. We need to make sure we get the right answer here, because they're going to take this number, we're going to use it in our formulas, okay? We have to be able to do this because our formulas only use certain units, okay? All right? Cross multiply, we get what? 101.325 times x, which equals 1 times 75. And if I want to do x, I know what you're thinking, this is a lot of work to get the same answer above. Well, I don't really care, as long as you get the right answer, okay? 75 divided by 101.325, and of course that works out to be 0.74. I didn't include units there. I'm kind of a bad person for not doing that. I should, okay? But 0.74 ATM was what you get it by doing that, okay? And again, I don't care, but you have to have a system that you're going to get the right answer, okay? And again, you know, you might say, well, I can do this, but it depends on the numbers you're given, okay? Good so far? You decide what's going to work for you. I'm probably going to do this most of the time because it's a little less work, I think, but that's up to you, okay? We're going to convert now 75 kPa into PSI, okay? So let me just write that down here real quick. 75 kPa into PSI, or as I like to call them, it's fun to say. So, again, I'd probably start with this, 75 kPa in this question here, times. Now, if I want to get into PSI, I know that I have to put this here and the kPa here, okay? Because kPa needs to cancel with kPa, yes? That makes sense? kPa and kPa need to cancel. What are the numbers I put there? You look them up. kPa number, if I'm standing on the shore in Vancouver, okay, we say on average it's 101.325 kPa. And then the person right beside me says, actually I disagree with you, it's 14.7 psi. Okay? We're going to put those numbers come from the back of the periodic table. Okay? You're going to take 75 times 14.7. You're going to divide it by 101.325, and you are going to get 10.8 something. Correct? 10.8. I'll just call it 10.8 psi. Because we only have 2 significant digits, I'm going to call 11.11 psi. 2 significant digits. Good? Questions? 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 All right. We'll do one more. Now we're going to do the next question there. The example that we had was, let's change 75 kPa. Obviously, it's the same number, so I get that. Into millimeters of mercury. Okay? And again, these are probably the most common ones that we're going to do. These are the 4 units that we use the most. Again, I'd start with 75 kPa. Now you say, well, is it always going to be this kind of thing? Well, yeah, you're going to take the number that you're trying to convert. So 75 or 40 or 28.8 or whatever, or 500. And you're going to multiply it by, you know, does KPA always go on the bottom? Well, if KPA is here, then yeah, KPA needs to go here, right? Because KPA has to cancel with KPA. So yeah, it has to go on the bottom, right? And the number that goes with KPA is 101.325. Again, from the back of the periodic table. The millimeters of mercury number is 760. Okay? Again, back of the periodic table. Let's look it up. So KPA and KPA cancel. When I do this, I think I get 562. Is that right? 562 millimeters of mercury, or 5.6 times 10 to the 2 millimeters of mercury. Okay? Two significant digits because we have only two in the question, yes? Okay? So that's something we need to be able to do. Yes? Questions, anyone? And again, it depends. Like, let's say let's just for example, I don't know, just pick a random example. Give me a unit, somebody. One of those four. Pick one. Yeah.
PA.
KPA?
No, PA.
No. Pick a different one. Give me one of those four that we just talked about.
Yes.
Okay. So if I want to change PSI into, what do you want to change it into? Give me something else, an option. Huh? ATM. Okay. So I'm going to take my PSI, whatever it is, make up a number. 4 PSI. And if I want to change it into ATM, I'm going to put PSI here, right? Boom, boom. Yes. And you said ATM. And we're going to put ATM here. Okay? It's a matter of now looking up what are those numbers. Look on the back of the periodic table. Okay? This is 14.7. This is 1. Okay? And again, those are constants, so we don't look at those. We look at this. That's one significant digit. I'll have one in my answer, whatever that happens to be. Okay? That's all you need to worry about. Okay? We're going to kind of do the same thing today. You're going to fill in a chart. I'm going to give you one of those 4, and you're just going to convert it into the other 3. We're going to get some practice doing that. Okay? Okay? Questions? Like I said, this is important because quite often our formulas only use, there's some constants with our formulas, and they use a specific unit of measure. Okay? All right? Next thing we're going to talk about is temperature. Now, we're going to talk more about this coming up here, but the temperature of a gas represents the average kinetic energy of the gas particles. It can be measured in Celsius or Kelvin. Okay? Have you guys heard of the Kelvin scale before? Anyone? Yes? Yes? Okay. So we talk about Celsius or Kelvin. Now, Celsius, of course, is Celsius. What is the Kelvin scale? Well, we'll talk a little bit more about that. And some people talk about where everything is absolute zero and all this other stuff, and that's true. We'll talk more about really what it means and things like that. But this is kind of the formula we use here. If I want to find the Kelvin, I take the Celsius and I add 273.15 to it. 273.15 is kind of the go-to number. Okay? It is on the back of the periodic table. It says 0 is 273.15. Okay? So that's one formula. You probably want to write this down. Okay? I know there's a formula there, but this will just make it a little easier. Okay? If you want to find Celsius, you're going to take the Kelvin and subtract 273.15. Okay? They're basically the same formula, by the way. I just rearranged them for the different letters. That's all I did. Okay? So again, if you can kind of remember this, if I give you Celsius, you add 273.15. If I give you Kelvin, you subtract 273.15. Okay? Or use a formula and figure that out. Okay? So this is where we need to be a little bit careful here. Now I think on your, is this right? 55 Celsius, is that what you guys have to Kelvin? Okay. So if I want to change 55 Celsius into Kelvin, I'd say, okay, I'm going to take the degrees Celsius and add 273.15. And after a while, this is going to become second nature. You're just going to do this automatically. You're going to know that number because we're going to use it over and over and over again. And I'm going to tell you right now that every formula we do this year, okay, and unfortunately it's not the same next year, or it's not the same in Science 10, but every formula this year involves Kelvin, okay? We do not use Celsius in any formula this year. We always use Kelvin. So you're going to do this a lot, okay? I'm going to put my 55 degrees Celsius here, and I'm going to add 273.15, and my Kelvin here is going to work out to be what? 328.15. Now, here's the issue, okay? So we'd be talking about 328.15 Kelvin. Now, that's what we probably use in the formula when we get to this stage, okay? When we add up the numbers, when we get to the formula, and we put this number in, we're going to use this number, okay? Unfortunately, for today, we're not going to use this number. Why are we not going to use 328.15 as our final answer? This is lesson 1, yeah? Right. So what should my answer be? Before you write it down, you might get it wrong. What should the answer be? How many people think the answer should be 328? Yes? No? What's your answer then? If you don't think it's right. Yeah?
328.2.
That's right. 328.2. And usually you put the K at the end for Kelvin. Okay? Why? Because when we add or subtract, we go based on the fewest decimal places. Yes? Okay? So just today, when we're filling in the temperatures, we're going to follow this. Okay? However, I'm going to tell you, unfortunately, you'll get one or two questions like this on the test. Okay? And that's fine. But everything else that we do, we just use the 328.15 because we're going to be basing it on multiplication and division. So we're going to go with whatever's in the question. Okay? If that makes sense. We'll worry about that when the time comes. For today, we're going to worry about fewest decimal places, just for these addition subtraction ones. And as you can see here, we have what? I think you guys have 335.6. Is that right? On your sheet for the next one? Yeah? Is that right? Okay, so I'm going to take 335.6 and subtract 273.15. And in this case here, I think I get what? 42.15, is that right? That'd be in Celsius. I think that's right, isn't it? 42.15? I'm just going based on memory here, so help me out. And again, in this particular example, I only have one decimal place, so I probably should only have, is it 42.15? No, it's not. 62.4, well, why didn't you say so? Who's keeping track of me here? Somebody's got to keep track of me. 62.45, that only has one decimal place, so we're only going to have one decimal place in my answer. Okay, so I'd say that's 62.5 degrees Celsius would be probably the best option for that. Okay, is that good? Again, that's only for today. After today, when we start using the formulas, we're going to go back and probably use like 328.15 probably is what we're going to put in the formula because we're going to round at the very end. Okay, good? Questions? Okay, I'm going to be quiet and you guys are going to do some work based on me today.